Hey there, students. In this clip, we're going to be going over an example on the mean value theorem. So before we get started, let's take a look at what the mean value theorem is. I'm going to be showing you a condensed version of the theorem, and then we're going to be looking at a graphical representation of what the theorem is saying. Okay, so let's write out what the mean value theorem is. So if f um, is a function is if f is continuous on a closed interval AB, okay, and differentiable on the open interval AB, then what? What does this tell us? Then this implies that let's try that again. Then there exists a C in the open interval AB such that f prime of C is equal to f of B minus f of A divided by B minus A. Okay? So the first part in black, that's the, this portion is the hypothesis of the uh, mean value theorem, and this is the conclusion of the mean value theorem. All right? Okay, so let's see what this looks like graphically. Okay, so let's say we have a function that looks something like this, and then let's say we have it's going from A to B. All right, so this is f right here. This is function f, and this is obviously f of A, and this point right here is f of B. Just by tracing it, you can see that that's the case. The initial condition says that the function has to be continuous. Basically, you don't have any discontinuity of any sort, jump removable or infinite discontinuity on the closed interval. So you can even have an endpoint discontinuity, such as an open interval or an asymptote. So it's continuous, as you can see here, and differentiable. So differentiability implies that it has no vertical tangent and it's smooth. Okay, smooth basically meaning that you do not have any cusps or corners on the interior um, in this interval. Okay, no cusps, no corners, no vertical tangents, and we've already talked about the idea of continuity there. Alright, so on the open interval AB, we see that it's a smooth curve. So this function actually satisfies the hypothesis of the mean value theorem. So we can then shift to the conclusion. So that tells me that there exists a C in this interval where the derivative at C is equal to the slope of the secant line through the endpoints. Alright? So what does that look like? So first thing we're going to do is let's draw what f of b minus f of a equals b minus a is. This is known as the slope of the secant line or the average rate of change. So let's sketch that. I want to draw that using a dotted line, okay? So this line right here, I'm just going to adjust it slightly. This line right here, that is the slope of the secant line through the endpoints, okay? So what the mean value theorem is saying is that there is going to be a tangent line to this curve that's going to have the exact value as the slope of the secant line, all right? So this line I just drew has a slope. If you look at the rise over the run, the rise right here, this is f of b minus f of a, just like algebra 2, f of b minus f of a, and this portion right here is b minus a. Okay, so the slope of this line is simply going to be this portion right here. So f of b minus f of a divided by b minus a. So that's the slope of this line. Think back to algebra 1 when you're doing y2 minus y1 over x2 minus x1. That's exactly what we're doing here. Okay, so this is known as the slope of the secant line. All right, this is f of b minus f of a. All right, so it tells us that there's a tangent line to this curve that is parallel to this secant line. Okay, so let's go ahead and see if we can find out what that line is. All right, so I have a clone of the line, has exactly the same slope. So I'm going to move this, preserve the steepness of the line or the slope, and move it until it's tangent to this curve. So right there, I'm going to move it down. Okay, so there you have it. So you see that this point of tangency right here, that's the C value that the mean value theorem says exists. So that this point of tangency right here, um, the slope of this line is going to be f prime of C. Okay, that's what the slope of this line is, and this is the tangent line. And we have found the C that satisfies the conclusion of the mean value theorem. And you notice, where is the C located? That C is in the open interval AB. All right, so that's the C that satisfies the conclusion of the mean value theorem. All right, so remember, you have the hypothesis as a requirement. It has to be continuous and differentiable. And then you can then find a C in this interval where the slope of the uh, tangent line at that point is equal to the slope of the secant line. All right. So one cool thing about this is that you can write the conclusion of the mean value theorem in different ways. Okay. So let's go ahead and write that down real quick, and then we'll try an example. So um, different ways to write the conclusion of the MVT. Okay, MVT is just the abbreviation for mean value theorem. So it can be written using rates. So using rates, what this equation is saying is that the left side, that is the same thing as the instantaneous rate of change. Instantaneous rate of change. So it says instantaneous rate of change, f prime of C is equal to, this expression right here can be viewed as the average rate of change. That's one way that the conclusion of the mean value theorem can be written. Another way that it can be written is using the line slope expression. So the slope of a line slope. All right, so using line, slope of a line, what does this represent? This represents the slope of the tangent line. Okay, so what it's telling you here, the conclusion is that the slope of the tangent line is equal to, this represents, this is this line we're talking about right here. This is the slope of the secant line, equals the slope of the secant line. That's another way of viewing the conclusion of the mean value theorem. The slope of the tangent line is equal to the slope of the secant line, where the point where you're evaluating the slope at is somewhere in the interval. Okay, and then lastly, we can use the prime notation. Actually, there's another one, prime notation, which is the one we have up there. F prime of C is equal to f of B minus f of A over B minus A. Okay, that's another way you can write it. And then you can use the delta notation or the change notation. So basically you can write it as d dx of the function evaluated at C is equal to delta f over delta x. This is the average rate of change evaluated on the interval AB. Okay, so all these four ways are the different ways we can write the conclusion of the mean value theorem. Okay, all right, so let's go ahead and take a look at an example. The instructions for the examples we're going to look at are as follows. Part A, we have to determine if the given function satisfies the hypothesis of the mean value theorem, That's the A part, and then the B part, if it does satisfy the initial condition of the hypothesis, it does satisfy um, the MVT's hypothesis, then you now have to find the C, that special C. It could be more than one. So the C or C's that satisfy the conclusion. That satisfy the conclusion. The conclusion. All right. So let's take a look at the first example. Example number 1. What if we have the function f of x is equal to x to the 1/3 plus 1. Okay. Now what kind of function is this? Or let's say it's on, we're looking at this on the interval -1 to 1. Alright, so this function is the inverse of your cubic function. If you remember, there is a special situation with the slope of the tangent line at x equals 0 for this function. If you don't remember, let me just generate a sketch of the graph for you, and probably that might help you remember what the situation is at x equals 0. This is the inverse of the cubic function shifted 1 unit up. Okay, so let's say that's 1 right there. So it's shifted 1 unit up. This function looks something like this. So going, let's say this is -1, and this right here is 1. Okay, so it's going to go up here and then here. This function is very interesting. It looks something like this, and then curves out like that. Okay, what happens with this function is that it has a vertical tangent at x equals 0. Okay, it has a vertical tangent. So if it has a vertical tangent at x equals 0, what does that mean? That means that f is not differentiable at x equals 0. So since it's not differentiable, remember the hypothesis requires the function to be differentiable on the open interval, right? So is it differentiable on -1, 0? The answer is not. F is not differentiable at x equals 0 because you have a vertical tangent. All right, so our conclusion is since f is not differentiable on the open interval -1, 1, it does not satisfy the hypothesis. Okay, it does not satisfy the hypothesis of the MVT. The hypothesis of the mean value theorem. Okay, let's just write it as MVT. Alright, so there's no C that satisfies the conclusion since this function fails the hypothesis. Alright, let's shift our attention to, this is part A, we did. Let's shift our attention to number 2. What if we had the function f of x is equal to 2x squared plus 4x plus 1 on the interval from -2 to 1. Okay? Alright, so let's do part A, the hypothesis component. The hypothesis, so for the hypothesis, the question that we're going to answer is f continuous on AB, and I'm sorry, is f continuous on the closed interval AB, and differentiable on the open interval AB. That's the question that we need to answer for the hypothesis. Okay, so if it's good for the hypothesis, then we have a C or C's that satisfy the conclusion. All right, so that's the question we're going to consider here. So let's take a look at this function f of x equal 2x squared plus 4x plus 1. What do we know about this? This is a graph of a parabola. It's a quadratic polynomial. What do you know about parabola or quadratic curves? They're smooth and they have no vertical tangents. Okay, they don't have any cusp corners, vertical tangents, and they're also continuous. Okay, this function is defined for all real numbers, so it's both continuous on the closed interval, -2 to -1, and then it's also differentiable on the open interval -2 to 1 because it has no corner cusps, or it's smooth, and no vertical tangents or discontinuity. So it checks, it satisfies the initial conditions of the mean value theorem. Okay, so how do we write that conclusion? Since f of x equals 2x squared plus 4x plus 1 is continuous on the closed interval -2 and 1, that means no discontinuities on this closed interval, and differentiable on the open interval -2, 1, it satisfies the hypothesis. It satisfies the hypothesis of the MBT. Okay? Hypothesis of the MBT. Alright, now let's shift gears and move to the B part. Remember, if a function satisfies the A part, then we can move on to the B part. If it doesn't satisfy the A part, then there's a conclusion to be made. Okay? So the conclusion now is that we have to find that C. What C are we talking about? The C that makes the C where the instantaneous rate of change is equal to the average rate of change on -2, 1. So a C where instantaneous rate of change is equal to the average rate of change. Average rate of change. Alright, so that's what we're going to be looking for in this problem, in the conclusion part. Okay, so what are we going to be doing here? We want to find, we want to basically find a C where find, let's change the color. Find C where f prime of C is equal to f of B minus f of A divided by B minus A. Alright, so that's what we want to solve. Alright, so let's break this up into two parts. We're going to first of all find f prime of C, and then next we'll find the f of B minus f of A divided by B minus A, and then we'll set both of them equal to each other. Okay? Alright, so let's start off by let's find f prime of C. Find f prime of C. F prime of C is basically the instantaneous rate of change. Okay, so how on earth do we do that? Let's recall our function. Our function is f of x equals 2x squared plus 4x plus 1. So to find f prime of C, we have to differentiate this function first, find f prime of x, and then evaluate it at C. Okay, so let's differentiate this function. F prime of x is equal to, using the rules of differentiation, this becomes 4x plus 4. So this is f prime of x. Then what will f prime of C be? F prime of C will simply be evaluating this function at x equals c, so we just substitute c into the x. So we have 4c plus 4. Now this is the left side of the equation and the conclusion of the mean value theorem. Now on the right side, what we're going to do, let's divvy up our workspace so we don't get confused here. On the right side, we're going to find the average rate of change, okay, or the slope of the secant line. So let's find f of B minus f of A divided by B minus A. Okay? Alright, in this problem, a is -2, because we have this interval right here. We're going from -2 to 1. This is a, the lower bound, and b is the upper bound. Okay, so where a is equal to -2 and b is equal to 1. Alright, so let's rewrite our function. F of x is equal to 2x squared plus 4x plus 1. Okay, so what on earth are we going to do now? Well, we're going to look for f of b and f of a, okay? So let's start with f of b, or f of 1. F of 1 is 2 times 1 squared plus 4 times 1 plus 1. Alright, using order of operations, 2 times 1 squared is 2 plus 4 plus 1. So 2 plus 4 is 6 plus 1 is 7. And then let's look for f of b, which is f of -2. That's 2 times -2 squared plus 4 times -2 plus 1. Using order of operations, we have 2 times -2 squared is 4, times these together minus 8 plus 1. We have 8 minus 8 plus 1 is positive 1. Alright? Okay, so let's go ahead and finish this off. F of, we're evaluating f of 2 minus, actually it's f of b is f of 1 minus f of -2 divided by 1 minus -2. That's the slope of the secant line. This is going to be, let's see, f of 1, we got 7 minus f of -2, 1. 7 minus 1 divided by 1 minus -2 is 1 plus 2, which is 3. So 7 minus 1 is 6. 6 over 3 is equal to 2. Alright? So that's the slope of the secant line. Alright, so we have both sides, the instantaneous rate of change and the average rate of change. Okay, so what are we going to do now? We have to find the c, right? So we have to set these two values equal to each other. So we need to set this. This is f prime of c, and this is f of b minus f of a divided by b minus a. We need to set them equal to each other. So let's write it down. Set f prime of c equal to f of b minus f of a divided by b minus a, and then we just solve. Okay? So what we're going to do is we're going to have 4c plus 4 equals, what is that going to be equal to? We're going to have it equal to the number 2. Okay? Alright, and then we'll solve for c. This is just a basic algebraic equation, and that will be the c that satisfies the conclusion of the mean value theorem. Alright, so to do this, just subtract 4 from both sides. You have 4c is equal to -2, and then you have c is equal to -1/2. Okay, so that's the c that satisfies the conclusion of the mean value theorem. Alright, so let's go ahead and box our answer. Alright, so what does this look like graphically? This is not necessary, but I just want to show you what the solution looks like graphically. So let's do the graphical representation of what we just did. So graphically. Alright, so let's look at the function on the domain that we talked about, okay? So the function was f of x equals 2x squared plus 4x plus 1. And we're evaluating it on the interval -2 to 1. Let's write this in vertex form, okay? So we're just going to complete the square real quick and then see how we can sketch the curve of this function. So I'm going to write this as f of x equals, I can factor out a 2 from these first two. Take out a 2, x squared plus 2x plus 1. And if you complete the square here, you're going to have this equals 2 times x squared plus 2x. You divide it by 2x squared, which is going to give you 1. Plus, since you added 2 times 1 here, you're going to subtract a 2 there also. All right, and then the function in vertex form is going to be 2 times x plus 1 square and minus 1. Okay, so that's what it looks like in vertex form. So it's a parabola that opens upwards, shifted 1 unit to the left and 1 unit down. All right, so that form just helps us make a sketch. Okay, so let's go ahead and sketch the graph of our parabola. So let's see what that looks like. 1, 2, 3, 4, 5, put it down here. So we shifted 1 unit to the left and 1 unit down, 1 unit to the left and 1 unit down. You have the vertex right there. So hold on for a second. I know the y-intercept of this function is one. Let's see if I plug in the y-intercept is going to be positive 1. If I plug in 0 for the x's, so it's going to intersect right here. And then if I plug in, what happens if I plug in -2? Because I'm supposed to evaluate this function at -2, that's the left endpoint. I think we already did f of -2. Let's go up. F of -2 is 1 also. All right. So there should be some symmetry in our graph because this is a parabola. So that's 1 point. So I'm graphing from -2 all the way to 1. All right. So if I plug in 1 into my function, we already know what the output is, right? Plugging 1 here is 2 plus 4 plus 1 is 7. We already did that before, but let's just do it again. So 1, 2, 3, 4, 5, 6, 7. So that's 7. And there's the other point of our parabola. Okay, so the parabola is going to, this is just a sketch, pardon me, I'm going to try my best here. It's going to look something like this. From here, and it goes all the way there. Boom. Okay, so that's the parabola. Now, the slope of the secant line that we found earlier is the line that connects these two endpoints. Okay, that's a secant line right there. And what we found out, what we did is we did this. Let me write it for you. Which one did we use our secant line? Secant line was blue. So this line right here, this is f of 1 minus f of -2 over 1 minus -2. This is the slope of a secant line. That's what we calculated over here. And what did we get that as? The answer was equal to 2. See this line? Rise over run. You rise 1, 2, run 1. What's the slope here? 2. You can see it pans out perfectly. Okay, and then the C, -1/2. This is not going to look too good, but let's just show it to you. This is the C that satisfies the conclusion of the mean value theorem. It's going to be somewhere here. If I drew this graph with a computer, guess what? The slope of the tangent line here will be, the graph of a tangent line right here will have a slope that's equal to this one right here. So what it's saying is that if I drew another line right here, they'll be perfectly parallel to each other. All right, so let's do it like this. So at this point right here, it's parallel. See this point? At -1/2, at that point, you have a slope that's equal to 2. So in this case here, f prime of -1/2 is equal to 2. So in this case, the slope of the tangent line, this is the tangent line, is equal to the slope of the secant line of the endpoints of the function. Okay, so that's basically what the mean value theorem is saying, and this graphical representation just shows you an additional way of looking at it. All right, so there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here so you can get updates to other cool clips such as this. Just post a comment to let me know what you think about this clip, and you can give me a thumbs up or like if you liked it. Thanks again for watching, and have a wonderful day.